Тынг, лайк Тесла.
We are drowning in a sea of electromagnetic noise. At least that's how it seems sometimes. What we saw there was my nice 40 meter HF dipole antenna and hooked up to a radio. When the antenna was unhooked, it was nice and quiet. When it was hooked up, there was a lot of noise. In fact, if you look closely, the S meter on the radio was reading a baseline noise floor of S9. And we can look and see exactly what that means. There's a standard for that. S meter means 50 microvolts at the receiver's antenna input, assuming the input impedance of 50 ohms, which is a correct assumption in this case. So 50 microvolts over 50 ohms. That's not a lot of power. Let's see what Wolfram Alpha says here. 73 dBm in watts is about 0.6 to 0.8x times the typical power output of a spleen cell. So though, that's not a lot of power if you wanted to do something useful like blink an LED or do something like that. So I've since taken that antenna down because with that much noise it wasn't much good for, receiving actual signals. S9 would be a pretty decent level for a pretty strong signal to come in. But if that's my noise floor, I wasn't able to do much with it. Anyway, we'll talk about ham radio antennas more. Let's switch back to my gigantic 60 cycle antenna. How much of this energy flying all around us is in the 60 hertz band? Okay, recall where we left things last time. We had this gigantic coil we wound here. It's about 5 or 6 feet in diameter, and it's made of 14 turns of this double-stranded speaker wire. So what we're going to do is hook up the two strands together like that. So effectively now we have a 28-turn coil. In the previous video we measured the inductance and so forth and the resistance of that. And now we're going to hook it up to the multimeter here, and we're going to measure and see, sitting here in the open air, indoors, in a house with electrical power, how much energy transfers into the coil. Now, I don't have the capacitors hooked up at all, but this is just a rough and ready check. And it looks like we're getting about 0.4 millivolts. Wow, that is not a lot. It's better than an S9 signal, but no, that is really weak. So even with the capacitors in the circuit, there just isn't a lot of energy there to build up. Now let's do a quick test here to make sure we're doing the right sanity test. Hang on, don't get vertigo. So I got this toothbrush charger thing. It's totally sealed, but it has a pretty good magnetic field coming out of it. So we're going to put that right along the cable here, right along our coil, and we're going to measure. There, it looks like a volt, a third of a volt. It's bouncing around a lot. This is not 60 hertz. But yeah, there it crossed over 2 volts and made the multimeter auto range freak out a little bit. So this is, this at least tells us that the coil is working. There's not a break in the wire or a short or anything like that. The coil is doing its thing. It's just that there's just not very much energy flying around for it to pick up. Okay, I wanted to validate that one more try. So I made a little baby coil here. This little son of a Papa coil. So it's got the same number of turns, 14, but in this case it's a 4-conductor wire. And you can see there's a little blue clip tucked behind there connecting 2 of the coils together. So it's a 28-turn coil, just like Papa coil. Oops, sorry about that. So let's get it hooked up to the voltmeter there and see what we're getting. The surface area is going to be a lot less, but the voltage across it, 0.4 of a millivolt, is surprisingly consistent. It's about the same. Okay, if there's any place that's going to have 60 hertz electromagnetic noise, it's going to be underneath these towers here. I'm not 100% sure, but I think these are 230 kilovolt lines that run right through the middle of Sunnyvale. So we're going to go camp out underneath these. We're in a little bit of a race against daylight here, but we're going to see what kind of measurements we can get based on proximity to these lines. And we're going to measure voltage and current so we can compute overall power. All right, let's do this. Here. So the best voltage reading I was able to get, reading 2.84 millivolts. This is basically directly under wires with the coil at a bit of an angle to capture the most lines of magnetics. Okay, so light is rapidly failing me, but here is the current captured, 3.14 or pi micro amps. So if we multiply this out, volts times amps, we get right around about 9 nanowatts, negative 50.5 dBm. So 23 decibel stronger signal than what we got on the S9 noise source, or in other words, about 200 times stronger. It would still take years of collecting this level of energy to get even a single joule of energy spent. Alright, so I get back to the house, I hang up the antenna on the bookshelf here, and look what happens. I'm getting 22, almost 23 millivolts of signal, way more than I got earlier in the house, way more than I got from underneath the power lines and everything. I'm going to compute the power on this, but it just goes to show, if you're using noise as your energy source, it's unpredictable. Yeah, this is without those capacitors hooked up still. And just as a test, let me try this real quickly here. Yeah, the voltage level drops way off when I hook up the capacitor. So it's possible some of this noise is not resonating at 60 cycles. It's also possible that something else has changed, like maybe the air conditioner running is affecting this. But let's talk about the levels of energy here. So if we're talking about nanowatts, is that something to be worried about? If you're living like right next to these power lines, would you care? While I'm talking here, I'm kind of hooking up the power reading here just to get some numbers. But if we look at the ARRL, the American Radio Relay League, they have an expert committee that looks at these kinds of things, and their safe exposure limits are generally in units like milliwatts per square centimeter. So a milliwatt would be 1,000,000 times, like 6 orders of magnitude bigger than what we were looking at for power density, and we were looking at an area much bigger than a square centimeter. You would have to be right on top of these power lines for it to be on the safe exposure limits. And two, those are for radio frequencies, and this is a lower frequency, which is less studied. What I'm concluding from this is, one, it's really difficult to capture enough energy from 60 cycle ambient noise to do much of anything at all. And two, it's well beyond the safety levels. Oh, and three, it's really amazing that our radios can capture so much information from such a weak signal. If you want to learn more about this, check out this ARRL resource page, arrl.org/rf-exposure. Lots of links and calculators and all kinds of things in here that can educate and inform. But for now, I'm on to my next set of experiments. Can't wait to see what happens with this. Smash that subscribe button.